there is a new data structure that we added in 14.2, which is Tabular. And the idea of Tabular is that it's highly efficient column-based data structure. So when you've got data that is rectangular, very often you get very homogeneous columns where everything in this second column is a date, everything in this third column is a string, and that allows you to then use the power of the compiler to be able to make these things faster and other various efficiency improvements. So minor but important improvements in terms of the data structure involved. You can see it with the tooltip here, but it's easier if I show you by asking for the schema for this database, this data, is that we now have a new geoposition representation. So here's the compiler representation of geoposition. But basically, this column now is optimized for storing latitude, longitude type positions, and will be more efficient in storage and more efficient in operation for that kind of data, which is really the last of the kind of most important data types that you get in these kinds of rectangular data that we didn't support, because we already have good support for numbers, strings, booleans, and dates and times. To go with that, we've also extended the kind of automatic support of Tabular. So this Tabular I've just imported is the London accidents database that I fetched from the UK government. And I can in a single stroke say, I want to plot just the geoposition column of that Tabular as a geolist plot and put all of those points onto a map. So without having to do some kind of take a column, normalize it, then geolist plot of the list, we've now got these data structures joining up seamlessly, and I can just say I want to geolist plot which column of which tabular, and it goes. And this is across several of the geo visualization commands. So I could take that same data and say do a geohistogram to find the density of accidents in London. And for those who are interested, Houses of Parliament is a hotspot, and so is a particularly annoying roundabout at somewhere called Elephant and Castle when I've studied this data. Now, another thing with Tabular is that Tabular is rectangular data, so it aligns very closely to relational databases. And we also, as part of the Tabular project, try to make sure that the kind of operations that you would consider doing in a relational database world are kind of seamlessly supported for kind of just elegant things like joins. So data joining was something that we had before, but we've now generalized it into a much more powerful join. Here's two tables. I've got some locations and names, and I've got locations and populations. And we already had the ability to join across a particular column. So I joined on the locations column. Now, you'll see here that I had three things in each, and they look at a glance the same, but my join only has two. Well, the reason is that if you look more closely, my Rome coordinates in one data set weren't exactly the same as the Rome coordinates in the other data set. Typical kind of problem that we're trying to join on things that are not unique tokens that like IDs that match perfectly. So now we have the ability to do joins across any comparison function across any columns. So what I could say here is I want to join those two tables on the locations column, but I want to consider those locations to be the same if the geo distance between the location in one table and the other table is less than 10 miles. So now the exactness goes away, and I can do this sort of fuzzy join, and I get a joined version of those two tables. And the same thing as you would do with a kind of SQL join type operation, but with this ability to call on arbitrary Wolfram language computation to make that decision about whether it's a match or not, instead of being on literal matches. Without this, you'd have to make a version of the table that rounded the coordinates or some other transformation to try and make them the same. Similarly, we have just an extension to joins now to do multi-table joins, so I can join multiple tables, three at a time with column-wise combine. Here I'm saying join across combinations where the first name and last name can be found in all three tables, and I can do an outer version of the same thing that goes to all permutations of first name and last name that match, so all the missings get populated as well. So the equivalent of inner and outer joins within SQL, but again, arbitrary sets of tables, not just pairs that you have to repeatedly join on. Now, Tabular is there principally as an efficient and elegant way of processing data, but as you'll notice, its output's kind of pretty. And when we have larger data sets, you've got things like scroll bars to be able to go through the data and storing it out of Notebook. So it's got a very nice interface on it. So we're also now starting to build out tabular as a presentational mechanism, and there's now styling mechanisms. So I can arbitrarily style cells in a tabular. So here I'm cycling the columns through 3 different colors. This cyclic actually is a new general computational thing buried in the language, where cycle part 3 will give us the same as part, but cyclic part 4 wraps around to the beginning again. So it just makes a nice, elegant language construct for these kinds of things, where we're saying we want to repeat the cycle rather than being 3 colors and then white after that. And we also have a couple of conditional stylings as well. So the conditional stylings are item value function and row value function. And the idea of item value function is we can say, I want this color to be, if the number is negative, color it red. So if I want to see rows in a profit and loss spreadsheet and I want to highlight the loss-making rows, I can now pick out the items that, according to, again, any Wolfram language computation of anything to do with the values in that of that item. And as you might guess, the row value function is the same kind of thing, but it works in a whole row at a time. So here I'm coloring the whole row if the profit key is less than 0. So the same essential condition, but I'm applying it to the whole row. So again, this can work out on any styling, font size, backgrounds, font colors, the frame labeling, all of those kinds of things can be controlled either in a fixed, cyclic, or conditional way, making presentation kind of easy and pretty now. Okay, slight change of pace. You've got the data. You can process it in all kinds of ways. What do you do with data? Well, one of the things we focused in on this time is issues to do with when you have noisy data, which is smoothing and fitting. Now we've supported since way back in the beginning the very standard things that you would do for data smoothing. So you can do things like moving average or moving median or other moving filters on data, and you can fit lines to data. What we're doing is now adding in a couple of localized versions of the same kind of concept. So if I open up some data here, here's my noisy data. We could do moving average on this in order to kind of cancel out the errors. But moving average has a tendency to blur features at the same time as squashing the noise. And what we have now is local model fit, which generates this fitted model. But basically, it is the fitted model is something that behaves like an interpolation function, but it's sort of based around a bunch of resamplings that gives me the underlying trend of that. And you can see it's sort of doing quite a good job of preserving bends that happen to be in the data at particular points. And it also comes with other advantages that it has, for example, uncertainty around it. So if I find what's the trend at position 1, it's not only giving me the value, which is 0.716, it says, but it's giving me an error bound on that as well. So what this is actually doing, something called local adaptive regression, or LOS fitting is often, or LOS fitting is it's often known as. And effectively what it's doing is it's taking short intervals, fitting a line to that, taking the midpoint of the fitted line and taking that as the estimate of the trend. So it's a little kind of sensitivity window of what kind of interval it fits that line over, but it's repeatedly fitting short lines and then taking the midpoint and treating that as the best estimator and taking the error bound from that. It works in higher dimensions, so we can take noisy data that we're doing, say, in this case, a contour plot on, and do a local adaptive fit on that to give me the denoised version in 2 dimensions. And again, it supports error bars on that. The other thing I said was fitting. And the problem with fitting is that you have to have a model. So that's fine if you know your model is we're fitting a straight line, or we know this is a nominal distribution of some data. But if you don't have a model in mind, you're kind of lost with fitting. What kernel model fit does is it breaks this into a piecewise fitting problem effectively. So I'm going to, for illustration, I'll use linear as the model that we're fitting to. And what you can see here is it's broken this data up and fitted separate straight line fits across different sections of the data. And there's a range of models here as well. So we could put something here like Gaussian, and you won't be able to see the joins now because it's a smooth model, but it's effectively doing the same thing. It's fitting a sequence of Gaussians to different sections of the data and joining them up. That gives us the advantage now of we actually have a model, so we can get the equation out of that model. And it also gives us, again, uncertainty around a particular any given point. And in fact, I think we can get an uncertainty model as well. So these are kind of just more powerful local versions of basically of moving average, type smoothing, and line fitting. But these are powerful techniques for real world data, for preserving features and dealing with things that don't have a simple underlying model. Of course, in the data world, there's always new formats. So there's a few new formats here: common log and extended log and JSON lines. These are all sort of logging formats. AVIF is, I think, an image video format. We've extended some of the existing formats to be able to import efficiently and directly into tabulars. And we've speeded up a few things I've already mentioned, Markdown. We're now at over 280 file and serialization formats that are supported for import and export. Something we introduced in 14.2 that is now sort of coming of age and becoming useful is data connection object, which is really just a simple unifying way of representing an external piece of data so that you can use it directly just as a kind of symbolic pointer. So while a lot of things you have a URL to point to data, very often you don't have a URL. You have to provide all kinds of connection and authentication information, and maybe a select statement in a database. And the idea is to package all of that up. So we now support databases as backends for data connection object, and a couple of services like OneDrive and Kaggle. So by way of illustration, actually, I seem to have already run this in this notebook. If I rerun it again, I'm now reaching into Kaggle, and I'm saying I want to connect to Kaggle and get this particular data set from Kaggle, which is whoever Joe Beach Capital is, has provided the top 10,000 Spotify songs, and I want to bring it in as a tabular. And so in a completely transferable way, I'm able now just to give you a reference that I can run and fetch that data in dynamically. And of course, this is a tabular, so I can do things like histogram a column of that directly. So there's the distribution of danceabilities of those 10,000 songs from Kaggle in 2 lines of import and visualize. But very much just a plumbing exercise for elegance and convenience.